We're now moving on to Unit 9B, which is all about ores and mining. There's a lot of pictures here that show kind of before, during, and after processes of mining operations. Let's start with the learning outcomes. Go ahead and pause the video and write down the learning outcomes for Unit 9B. I want to start with a few quick definitions that will address learning outcome number 5, which had a number of definitions. First of all, what are renewable resources? Well, I feel like we've talked about this a long time ago. Renewable resources are those that we have sort of an endless supply of, at least on a human time scale. We have plenty of this kind of resource. Examples are sunlight, wind, water. We have plenty of these things. We're not going to run out of them. And note that mineral resources do not fall under this category. They fall under the category of non-renewable resources, resources that we do not have an endless supply of, and especially on a human time scale. Now, of course, these things formed over geologic time scales over millions and millions of years. So even though I say once they're gone, they will eventually come back. But for example, it takes millions and millions of years for a coal deposit to form. So once we've used it as humans, it's gone. But in millions and millions of years, there'll be some more. Examples are fossil fuels, like I was just mentioning, metals, minerals, and even soil. In this day and age, we are using faster than it naturally forms. Another few definitions include metallic and non-metallic mineral resources. This one should be pretty straightforward since we've studied minerals. Metallic minerals include lead, copper, tin, iron, zinc, all the different minerals that we've looked at in lab that have a metallic luster. Non-metallic mineral resources are still resources. They're still things that we find valuable and useful, but they don't have metallic minerals in them or metallic materials. They might be gravel, sand, limestone, evaporate minerals, and even phosphorus, which is important for fertilizers. Another thing I want you to be clear on are fossil fuels. Fossil fuels are energy sources that are created by ancient ecosystems or life. Coal, oil, and natural gas are all examples of fossil fuels. And you learned about these in the short 6-minute video that you watched called Coal, Oil, and Natural Gas, in which you learned how these different things are formed. You also learned a little bit about how we access each of these different kinds of fuels, as well as which of these produce the most carbon dioxide pollution. Ores and ore minerals are not fossil fuels. They are not created by life, but they are concentrations of ore minerals as we've looked at in lab. An ore is the rock that actually contains the ore mineral, and an ore is a rock that has a large concentration of that ore mineral. So, for example, all rocks have a little bit of gold in them somewhere, but it might be 0.0001%, not an amount that you can extract economically and usefully. But an ore is a rock that has a large concentration of gold or some other thing that we want. And that thing that we want is usually a metal, and that's what we call the ore mineral. Ore minerals are often sulfides, oxides, carbonates. They're not often silicates. Examples that we looked at in lab include bauxite, hematite, galena, and the other ore minerals that we looked at in the ore mineral lab. And you also learned about ores in the short little video called Ore Minerals. So here's the outline for what I'm going to talk about today. And this is going to be divided into this and another video because it's a little bit longer than 12 minutes. What are the natural processes that concentrate ore minerals? Just like I said, gold is probably present in a lot of different rocks. But what are the processes that concentrate gold into large enough deposits that it's worthwhile for us to go out and mine? And then second, what is involved in mining? So we're going to start by looking at what are the processes that concentrate particular minerals in the crust. Over here I have some common elements and their average concentration in the continental crust. Oxygen and silicon, which if you recall are the most common elements in the crust, are very abundant, and ppm means parts per million. And so we have oxygen and silicon, and that's why the silicate minerals are so common. And then aluminum is fairly common, but things like copper, silver, gold, platinum, they are very, very rare when it comes to their average concentration. Over here, we have all of the elements in the periodic table from 1 to 92, which is uranium, and then their abundance in the crust. And notice that this is a logarithmic scale. So every time you go up, you're going up by a factor of 10. So we have the most common ones up the top, oxygen and silicon. The rock-forming elements are in this dark green pattern here. Additional ones that are fairly common are here. And then the ones that are down here, gold, platinum, iridium, palladium, these are the rarest metals of all. And these are the ones that we often need in industry. These are the rare earth elements, which we've talked about before, aren't necessarily rare when it comes to comparison to something like gold, but they are rare to find in the crust overall. And they are very important in electronics and magnets and things like that. So there are two main processes that concentrate ore minerals. I'm going to go over this really quickly. There's lots and lots more that we could talk about, but we're not going to have time. So two sets of processes are related to magma chambers. The other two are related to weathering. So let's look at these first two. The first one, the category is called magmatic segregation deposits, which is a fancy way for saying that magma chambers somehow separate ore minerals from magma, or they separate the magma from the ore minerals. Somehow there's a separation involved in the process of the magma chamber cooling or the magma chamber mixing. And the types of ores we get are things called cumulates, immiscible melts, pegmatites. I'm not going to ask you about that. And then these are some examples of metals. So let's just look at a cartoon here. Here's a magma chamber, and we've talked before about how sometimes we have certain minerals that sink because they're more dense than the rest of the magma, and they settle out and they form a concentrated layer. And so that could be a concentrated layer of, if we go back, chromite, ilmenite, magnetite, one of those types of metals. We also have something called an immiscible melt, and this involves two kinds of liquids that don't mix. That's what immiscible means. If you think about oil and vinegar in a salad dressing, right? You shake them up. Do they mix? Or you could think of oil and water as well. They don't mix, right? The oil goes to the top, the water goes to the bottom, or the vinegar goes to the bottom. They're immiscible. And it's because they have different densities. So sometimes that happens with magma. And one liquid sinks and the other liquid rises. And it separates out and you end up with a layer of one type of material and another layer of a different type of material. Another type of separation that occurs related to magma chambers are hydrothermal deposits. And these are related to the heat at the top of the magma chamber that heats up groundwater. So up here in this region, where this very hot material is heating up groundwater, it can actually precipitate out brand new minerals from the water. So let me show you. Here we have some magma chambers, and there's hot geysers and groundwater. You can think of this like Yellowstone. And the groundwater might dissolve metal oxides and sulfides from the rocks. And then the heated magma comes in and precipitates it in the joints or the cracks as metal ores. And here's an example. This is quartz, and then also we have pyrite precipitating in what's called vein deposits. Here's a major copper mine that was formed this way. And in fact, this is the Bingham Copper Mine in Utah. It is the largest man-made excavation in the world and the deepest open pit mine in the world. It's 3/4 of a mile deep. You could fit 2 Sears towers in here, apparently. And if you look really closely, there's a truck down there. There's a truck right down there. This has produced more copper than any other open pit mine in history. 19 million tons of copper. And so that was formed by this hydrothermal process. Another type of hydrothermal deposit that is a very different process is at hydrothermal vents at mid-ocean ridges. Remember, we talked about how you can have black smokers at hydrothermal vents at mid-ocean ridges, and they build their own sort of chimneys. These black smokers precipitate out minerals from seawater, and this is what the chimney looks like if you can take a piece of it and cut it in half. And so that smoke right there is really just hot water coming up through this chimney, and there's a little side chimney over there. And so this is a deposit that was formed by hot water. Hydrothermal water is hydro, thermal is hot. Two processes related to weathering are shown here. There is a residual mineral deposit, and this is basically related to chemical weathering processes that have broken down rock and redeposited the material somewhere else. An example of this is the formation of the mineral bauxite, which we looked at in lab. So we have aluminum-rich intrusive rocks at the surface, and they're chemically weathered, and it forms a material, a residual soil that is very rich in aluminum. And so we get our bauxite ore, and here is an example of what it really looks like. This is the cartoon, but we get this soil that's very rich in aluminum. Finally, we have another kind of sedimentary mineral deposit that includes the banded iron formations that we looked at way back at the beginning of the semester, evaporate minerals like salts and gypsum that form when water evaporates out, and then also placer deposits. This is a banded iron formation. Remember, these are Precambrian formations that form when iron and oxygen in the ocean combine to form iron oxide, and that this is something that doesn't happen anymore because all of the iron has been taken out of the oceans and the oxygen has gone out into the atmosphere. Over here we have placer deposits, which are what some people use to find gold. So if you imagine you have water coming down the mountain and it's carrying sediment with it, well, gold is very heavy compared to quartz or feldspar sediments. So it preferentially falls out of the water stream and it gets placed in places where water is lowest, and that tends to be on the inside of curves. And so that's where your heavy minerals are, and those are called placer deposits. And so that's where people tend to look for gold, and that's a sedimentary process that naturally takes gold or other heavy metal elements and sorts them and concentrates them so that we can go collect them. Next up is mining.